Good afternoon, everyone. In this video, I will illustrate how to create an adjacent matrix for the graph here above. Well, the adjacent matrix is already created, but I will illustrate just for to save some time. I had pre-created it, so I will illustrate how it is done. Now, this graph here, it has 16 vertices, and each of these vertex would represent a column in the matrix here and also a row. So it's like a heading. So it's a column heading and a row heading from A to P. Okay, so how it works is that for each of the edges that is connected to the node, it would be represented in the matrix down here. So if A has a node, an edge, sorry, that is connected to B, we place a 1 there. And if it doesn't have, like in this case, A doesn't have an edge that connects to itself, so we put a 0 there. So in all the instances where there's no edges connected to the node, we put a 0 there. And for where it is connected, we would place a 1. So for example, node A here has 3 edges. So it has one that connects to E, one to F, and one to B. So I will come on the column A now, and I look for B. We place a 1 there. Go down to E, a 1 is placed there, and F, a 1 is placed there. So that would represent the edge that is connected from A. All the other spaces, I put a 0. And I would also do it column, then row. So we place a 1 on the B here from A, a 1 under E here, and a 1 for under F, and every other space as a 0. So we look at node B. It has connected edges, adjacent edge connected to A, as it adjacent to C also. So it means that we have 2 1s in that column and that row. So 1 to A right here and 1 to C. We'll go over here, 1 to, connected to A, 1 to C, and everything else is 0. And we're going to do it for all of them. So C has 3, and C has 1 connected to B, 1 connected to D, and 1 connected to F. Everything else is 0. Go across B, D, F. Everything else is 0. To D, we have 2, 1 connected to C and 1 to G. Here it is. 1 to C, 1 to G. Everything else is 0. 1 connected to C, 1 to G, everything else is 0. E has 2, 1 to A and 1 to I. There it is, a 1 there. Down here, a 1. Come over here, going across. 1 is at A and 1 is at I, and all the other spaces are 0. F has 3. So 1 connect to C, 1 to A, and 1 to J. So A, C, J. All the others are 0. A, C, J, all the others are 0. So we go on to G now. G has 4 nodes, 1 to D, H, J, K. So D, H, J, K. Everything else is 0. We'll come across here. D, H, J, and K, and everything else is 0. Look at node H, 2 adjacent edges, 1 going to G, 1 to O. So we look for G here, 1 is there, 1 is at O, everything else is 0. We come across and we ensure that it's the same thing. A 1 is at G, a 1 is at O, everything else is 0. And we go now to I. So I has 4 nodes, E, M, N, and J. So 1 connected to E, 1 connected to J, 1 to M, and 1 to N. Everything else is 0. Come across, 1 at E, 1 at J, 1 at M, 1 at N. Everything else is 0. We go again now to K. K has 2 nodes. I'm sorry, we didn't do J. We stop at J. So J has three, one to I, one to F, and one to G. So J, one to F, one to G, one to I, everything else is zero. Look at J across now. One at F, one at G, one at I, everything else is zero. K, K here has two nodes, one at G and one at O. Here it is, here it is. One at G, one at O, everything else is zero. L, L has one node and that is at P. So everything is zero until we reach P. Same thing across until we reach P. All right, so let us look at M. It also has one node and that is connected, one adjacent edge and that is connected to I. So let us look at M. Right under I, we have the one and everything else is zero. Come down M, the one at I, everything else is zero. At N now has two adjacent edges, one connected to I, one at O. So we look on the M, on the N, sorry, and we place a one, sorry, right here on the I and one on the O, everything else is zero. We go across on the I, on the O, everything else is zero. Okay, so we look at O, and O has four edges, one going to N, one to K, one to H, and one to P. So we are going to ensure that the four ones are there, one at H, one at K, one at N, and one at P. Same thing across here, one at H, one at K, one at N, and one at P. And then our last node, P, has two edges, one at I and one at O. So we go down, one right here at, I'm sorry, not I, that was L. Right here at L, I place a one, and at O, another one. We come across, and we have a one at L and a one at O, and everything else is zero. So that concludes our adjacent matrix. Moving on now to our insertions or sort, and we're going to be using the insertion sort algorithm. What this algorithm does is to it stores the item that is to be moved. It moves items, so it's like a swap. You take out an item that doesn't belong and you swap place with it. You would shift, you decide where is the correct place for it to go. So you would put it in the temporary variable, and then when the decision is made, you would swap place with whatever is there and shift everything else to the right that is greater than it. So let us look at the first two numbers in this list. There are 20,000 and 51. So we would have seen that 51 is smaller than 20,000, but 20,000 is in the first place. So we remove the 51, we put it in the temporary variable, and we shift everything down to the right and place the 51 at front, right? And then next we look at the 2600. It is smaller than the 20,000, but yet it is greater than 51, so it would go in between the 51 and the 20,000 and it comes right here. So everything else is shifted to the right. The next number that we look at is the 10 right here. So we're going to take the 10. We see that it is smaller than all the others that are in front, so we know definitely that it will go in the front space. So we after placing it in the temporary variable, we shift everything to the right and place it at the front. Okay, so next in line is the 94. So we take the 94, put it in the temporary variable, and we analyze the others to see where it falls. It has been determined that it would fall between 51 and 2600. It's greater than 51, but it's less than 2600. So from 2600, everything would be shifted one space to the right, and it's placed right here, and then these two would remain. Next, we'll take 84, place it in the temporary variable, and we would decide where this should go. So 84 is greater than 94, but it's less than 51. So it goes right here where the 94 used to be, and everything else would have been shifted to the right. The next number that we look at is 71. So 71 is greater than 51, but it's less than 84. So it would go in the space where the 84 is. So after taking it from the temporary variable, it will be placed here, and everything else is shifted to the right, and then the the 10 and 51 would remain in front. So the next number that we look at is the 30. So 30 is less than 51 but greater than 10, so it will go in the space where the 51 was. The 51 and everything else would be shifted, that is greater, would be shifted to the right, and hence the space created for this. All right, so the next number now that we'll take is the 87 right here. And the 87 is greater than 84, less than 94. So definitely it would be placed in between both of them in the space where the 94 used to be. So 94 and everything else to the right would be shifted to the right to make space for the 87. The next number that we'll look at is 47. 47. So we place 47 in the temporary variable, and we decide where it's supposed to go. So 47 is greater than 30 but less than 51. So it would be placed right where the 51 was, and everything else would have been shifted over. The next number we'll look at is 62. 62 is greater than 51 but less than 71. So 62 would be placed where 71 was before, and everything else would be shifted to the right. The other numbers in front would remain. So then, and then the next number that we'll take, put in the temporary variable, is 35. So 35 is greater than 30, but less than 47, so it would go where 47 was, and 47 and everything else to the right of it would be shifted to the right to make space for it, and the 10 and 30 would remain in front. The next number would be 12. So 12 is greater than 10, less than 30, so it would take the space where 30 used to be, and the 30 and everything would have been shifted to the right to make space for it. The 10 remains in front. Now the last number is 8, and 8 is less than all the other numbers. So we would, after placing it in the temporary variable, we would place it, shift everything to the right and place it in front here, and then everything would fall into place, and there we would have our numbers arranged in ascending order by using our insertion sort algorithm. And the asymptotic notation for the insertion sort, it is a mathematical notation that is used to describe the running time of an algorithm. Now, it is denoted by the symbol O, big O, times n square. And n here would represent the number, the input size. So it also has what we call worst case analysis, best case analysis, and the average case analysis. In the worst case, what it does is it performs n-1 swaps for each element that is in the list, and that would result in a total of n times n-1 all divided by 2 swaps. So it looks at the time that it takes to traverse the list to make the changes and to place the numbers in the correct order. And the best case analysis now, it will perform only n-1 comparisons, and that means it would take less time to traverse the list, because in the best case scenario, the list would have probably be maybe in perfect order, probably almost sorted, so it would not take so much time to compare and to do the swap or the change over. So um, it would take that time. So here end my presentation. I thank you.